Welcome to our presentation. I am Birte Heinemann from the Learning Technologies Research Group at the RWTH Aachen University. I will present a group work. I will be the person talking, but you will see it is a team investigation. Especially in the beginning, we got help by talking to other people, for example, our computer graphic experts, developers, researchers and learners. But first things first, let's start with our vision. Why do we want to teach the concepts of the rendering pipeline in virtual reality? Starting point was a wish to teach something basic, to motivate students and to trigger enthusiasm. Virtual reality is a good technology to transport fascination about 3D and 2D content, and it provides easy access into the field of computer graphics. Let's talk about the content and the learning goals. Students should learn about points that are connected to triangles, how we create objects using basic geometry, and how objects like this elephant are created. Students follow the steps of the pipeline, learn about the perspective, clipping, light and shadow. As a result, they understand the basics of computer-generated graphics. They get an overview of the simplified pipeline we use in our Computer Graphics Foundation lecture. Our goal is to make the conceptual knowledge tangible and interactive. And thinking back when I was a student, and with many thanks to my own computer graphics teacher for making her learning objectives transparent, we also wanted to make the role of math clear. Beside these more obvious goals, this application could help especially students with a low visual spatial ability. It could later be used to scale teaching and to activate our old students. But we not only want to support teaching and learning. Our vision is also to learn about learning. For this, we follow the learning analytics way. We collect data, such as gaze, interaction data, movement and gestures. Till this talk, we also played around with keyword recognition. Using this data, we are able to get a deeper understanding of the learner's behavior and to evaluate and improve our application. That perfectly leads to how we developed the application. We started like many other software development processes. We created personas, talked to stakeholders and get familiar with the related work. Building on this, we started with an iterative process and smaller define, make, learn cycles, which are embedded in a research methodology typical for education, the design-based research. Following this approach, we grounded our research on constructivism, experimental and case-based learning, and developed it in a learner-centered way. Finally, we'll come to the results. We decided to create a guided tour. The robot in the middle accompanies the learner in the scenario, which is parted in stages. Every stage refers to one step of the rendering pipeline. This modular approach is great for iterative research, development and improvement. In this way, we can develop a good didactic abstraction and control the different interactive tasks. This picture shows a panel which the learner uses to navigate through stages. Actually, we are in the final step, where the learner sees a final 2D image for the first time. On the left, you can still see the scene in 3D. Let's take a deeper look at the concept we included in the learning application. This panel shows the steps of the pipeline which are implemented as stages of the guided tour. We use a simplified rendering pipeline, in line with the introductory lecture of Professor Koppelt in our university. I'll shortly show you the parts of every stage. First of all, we introduce the locomotion and the selection technique in a short tutorial. The learner has time to practice both and could do it as often as he or she likes. After that, we start the guided tour with an introduction. Since the first version, we enhance the dialogue to convey the bigger picture, motivate the learner, and explain the learning goals. In the next stage, the 3D geometry, we get down to business. The learner can observe how the TRS matrices are computed. This stage is available in two versions, an interactive and a non-interactive one. After this, we start with some basic knowledge concerning 3D objects. Like I started the talk, to teach how 3D models are created. The mesh of the Stanford bunny is shown, followed by some interactive tasks. Finally, the learner explores 3D models with the goal to rebuild an octahedron with points, lines and polygons. And with this basic knowledge, we'll start with the transformation step. The robot Kyle explains that the resulting 2D image depends on settings of the virtual camera, the frustum, and the parameters. The manipulation of these parameters can be used in the most following stages. On the left, you see that there is a video in the VR scene, as soon as the learner gets the task to change the near and far plane. We use this mechanism for some interactive tasks. The videos show how a learner attempts to solve the task. The next stage, clipping, is required to not render scene objects outside the virtual camera's view space. Those objects are visualized in a turquoise color. It's possible to change the settings like in the stage before and to observe which polygons are not to be displayed. There are two alternative ways of visualizing the clipping, which could be changed by clicking a button on the controller. The first one shows the primitives that intersect with the boundary of the view volume and that are clipped. The second one hides the turquoise parts. The rasterization stage is actually focus of a design, make, learn cycle. In the beginning, this stage was designed like a lecture. Kyle explains that the visible primitives of 3D geometry create fragments, which are used to compute potential pixels. The lighting stage shortly presents the effects of light and that it is important for color and the impression of depth. This step is drastically reduced to the fundamental knowledge. We experimented with teaching content matching this guided tour. This can be experienced in optional other scenarios not included in this original pipeline, as it is not required for reaching the actual learning goals. In the texture stage, a 2D image, the texture of Kyle, is shown besides the non-textured 3D model of the robot. He explains that it is possible to model the surface with detailed geometry, but textures are a way to reduce the complexity of a model and to paint details on simpler geometry. This stage is also available in two versions for doing research and learning. This one and another one where the learner uses spray cans to interact with the robot texture and the model to observe the connection. The visibility stage finally explains that the depth value of the fragments and the depth value of the frame buffer at the position of the fragment are compared and that only visible fragments become pixels at all. In the last stage, the 2D image, as a result of the previous stages, is shown, and the learner is invited to explore the scene until he or she is done with experimenting. A teleport point is just in front of the 2D image so that the result can be viewed from the camera's point of view. If the user points to the image, it becomes transparent, and so the individual steps of the pipeline become visible again. The learner is able to compare the image with the transformed 3D geometry. Let's talk about the evaluation and connect it with previous findings and related work. The nice thing is, we have already completed several evaluations. The difficulty is to explain them in a talk on point. For this reason, I will now summarize the most important results from small development cycles, but especially from the two larger studies. In addition to tests with learners, we also gathered feedback from experts who tested the application. We collected around 150,000 statements from 24 participants in 2 evaluations. VR learners spent 29 minutes on average within the application. For the 14 desktop users, it was 9 minutes less and showed less variance in usage time than the VR users. This effect is probably biased by some experimental design things. But also other reasons can lead to this. The information from the interviews lead us to believe that the 3D intensive interactions, such as building your own models, are more interesting and motivating in virtual reality. Desktop users created fewer triangles, on average 4, while VR users created 10. VR users spent on average 6 times longer in the geometry stage and even 7 times longer in the image stage. The results, especially from the verbal feedback of our learners, fit to research findings by Oberdorfer and Latuschik, who created a learning environment for affine transformations. They found indicators that virtual reality is beneficial compared to the desktop version. An initial evaluation of the head movements from the VR users shows that users nod significantly more often than shake their heads, a gesture that we could interpret as an indicator of understanding under certain conditions. Connecting this with the gaze or interaction data, we are able to observe nods when users finished a task or read text. Notable is that the different VR experience levels had a clear impact on the behavior of the subjects during the studies. While people without prior experience were more static and did not move and interact that much, experienced users moved around the objects and tried different buttons. Another aspect of future research is to investigate in the effects of the visual spatial ability and if the application is particularly helpful for certain groups of learners, like González Campos et al. Found in their study 2019. They trained students with 2D and 3D geometric transformations with using virtual reality. Last point for this talk. We made an unintended observation. The data collection of the second evaluation took place at the beginning of the semester. The students were taking a class on learning technologies, with the learning goal to understand how to design learning applications. We didn't expect them to talk about the learning contents of the rendering pipeline, but the students remembered details and used the answers in the exam's questions. Not really surprising, but a question for later research, is that indicates a positive learning outcome after a longer period, especially for the interactive tasks. These findings are in line with Huang and Liao, who showed the chances of interactivity in the virtual reality for learning in 2018. Let's sum it up. RePiX VR is about learning. It's a modular and open source application created to teach concepts of the rendering pipeline in an engaging and interactive way. We included data collection to support learning and give feedback to students. It's fun to work with the students. We tried to develop a user-friendly application, not only for teaching, but also to learn about learning. Thanks for watching. We look forward to meeting you at the conference.